Hello everyone, my name is Fernando. Today I'm going to talk about near linear time decoding of Ta-Shma's codes via splittable regularity. This is joint work with Shashank Srivastav and Madhur Tusiani. So as we said, the goal of the talk is to present this near linear time decoder, and we are going to use pseudo-randomness techniques. More precisely, we are going to base our techniques on weak regularity decompositions. And let's start from the basics. So binary code is a very simple object, just a collection of strings. So here we have our space, and the dots are the code words, binary strings. And we have two important parameters. The first one is the distance, which is the minimum of the normalized Hamming distance, or overall possible pair of distinct code words. So that's the minimum distance of the code. And the second one is the rate, and the rate is quantifying the size of the code. So we take the size of the code, we take the log, and we divide by n. So it's capturing the fraction of information symbols, useful information symbols. So it's quantifying the size of the code. And those are in natural tension. So the higher the rate, typically the smaller the distance, and vice versa. So that's typically very easy to see in the picture. So on the left, we have a lower rate code, and on the right, we have and we see that we can achieve a larger distance. And on the right, if you try to pack more code words, then the distance decreased. So they are in natural tension. And the natural question would be, what is the best trade-off between size, the rate, and the distance of a code? And this question was investigated since the 50s with Gilbert and Varshmov. They established non-constructive bounds, such that here we have this curve called the GG bound. And below this curve, we know that there are codes achieving this combination of rate and distance. But their proof was not constructive. They are not teaching us how to explicitly construct such a code. And what is interesting about this bound, about their proof, is that it's not too far from being optimal. So a little bit above, combinations of rate and distance above the red curve are impossible. So we have impossibility results. And in this talk, we are going to focus on the large distance regime for binary code, and this means distance half minus epsilon. And again, the GV bound is nearly optimal. And what does that mean in this very large distance regime? So the GV bound established that rate epsilon squared is achievable. And we know from the impossibility results that the best that you could hope for is an extra log factor. Okay. And it took many years for an explicit construction to emerge. And in 2017, Ta-Shma gave a beautiful construction and achieving almost a rate very near the GV bound. So here you have a rate of epsilon squared plus a little old term that goes to zero as epsilon vanishes. So it's a very nice result. And the question is, how efficient can we decode Ta-Shma's codes? And in this talk, we are going to treat this case of linear time decoding of Ta-Shma's codes. So that's going to be our main result. And more precisely, we have the family of Ta-Shma's codes. They have a rate that's near optimal, it's close to the GV bound. And the running time is going to be near linear in the block length. So here we are hiding polylog factors in the block length, and also some factor depending on epsilon. That's worse at most doubly exponential. Okay, very good. And our techniques, as we said, is going to be based on a pseudo-randomness approach. And that's why we have this slot machine here. And previously, we had a decoder, an efficient one, but the running time, this previous approach was based on the sum of squares hierarchy, which is an STP hierarchy, and it's known to not be extremely fast within polynomial time. So we got a polynomial time algorithm, but with a large exponent. And the exponents in some cases was also a function of epsilon. So it's a very powerful hierarchy, very nice, very useful to show polynomial time solutions, but it's also slow. So we represent it as a separate turtle. And now let's move towards Ta-Shma's construction, and we need to talk about this connection of expanders and codes. And an expander is very useful to amplify the distance of a base code. So we can start from a good code with possibly not wonderful parameters, and using the pseudo-random properties of an expander, we can boost this distance. And how we're going to do that, we can think that we're going to take a bipartite graph, and here we have the nodes on the left and the nodes on the right. The nodes on the left are indexed by 1 up to n, and the nodes on the right are indexed by tuples of n to the k. And if you take an arbitrary word, we can associate its symbols with the vertices, right? So Z1 is associated with the first vertex, Z2 with the second, and so on and so forth. And on the right, what we're going to do, we are going to, for each vertex on the right, we look at the neighbors. So this is neighboring Z1, Z2, and so on. And then you're going to take the XOR of the associated symbols here. And for each such node, we compute the XOR of the associated symbols. And this is going to give us a new word. And as we conduct this process, typically the size of W's is larger than n. And we are incurring a rate loss. But at the same time, we hope that we are amplifying the distance. And there is this tension between the two. So the trade-off is important. How much we are losing rate and how much we are gaining in terms of the distance. Very good. And these authors, they were the first to study this kind of amplification using expanders, and it has many applications in coding theory. And let's take another moment to formalize it better, the direct sum, because it's crucial here. So here we have a word Z in F2 to the N, and we have a collection of indices. And the direct sum of this word is going to be a new word, possibly on this larger space, F2 to the W, such that for each tuple, we are going to take the XOR of the symbols of Z associated with the indices in the tuple. So we take ZI1 all the way to ZIK. And we are going to use this notation. We are going to say that Y is this sum, the direct sum using collection W of the word Z. Again, we have our bipartite graph. On the left, we associate the symbols of Z with the vertex on the left, and on the right, we collect the XOR of the neighboring symbols. Very good. So that's the direct sum. And it's going to be more convenient to talk about bias, which is a closely related notion to distance. And the bias is just the difference between zeros and ones in the word in a normalized way. And the bias of the code is just the largest bias that you see. And if the bias is small, it implies that the code has large distance, okay, assuming C is linear. And to give some examples, if you have all zeros, we have full bias, bias 1. If you have all ones, you have full bias. And when the word is balanced, has half zeros and a half fraction of zeros and a half fraction of ones, the bias is 0. So, and in order to study the power of a collection of tuples in reducing the bias and amplifying the distance, Ta-Shma introduced this notion of paired sampler. And it's indexed by 2 parameters, epsilon 0 and epsilon. And we think that epsilon is much smaller than epsilon 0. And this collection is going to be a paired sampler for all the words, as long as the bias is not too large, the direct sum of this word used in the collection has a much smaller bias epsilon. So that will be a paired sampler for us. And one way of constructing paired sampler is to take a bound degree expander graph, take the collection of all k-1 length walks, and use those as your tuples. So this gives a paired sampler, and the parameters are quite nice, but not optimal. So it achieves rate about epsilon to the 4. And Ta-Shma, what he's going to do, he's going to de-randomize the choice. Instead of choosing all walks of length k-1, he's going to choose a much sparser set. And nicely, this is going to achieve the near optimal parameters that we discussed before. And he used nice techniques related to the zigzag product. And now let's go back again to see what the code in direct sum looks like. And if you have seen some versions of the previous approach, I apologize, but I'm trying to make this talk self-contained. And the informal setup is as follows. We start with a base code with potentially poor distance. We have a collection of tuples for our direct sum construction, and then we are going to construct the amplified code using the direct sum that you have, and this amplified code hopefully has large distance or small bias. And now suppose that we start from a pristine code word in this distance amplified code, and it gets corrupted to some y tilde, still in the unique decoding ball, centered at y star. And what we're going to do here is, in the decoding task, the decoder only has access to the corrupted word, right? The corrupted code word. And the claim is that decoding corresponds to solving a specific max k-XOR equation. So what we're searching for is a Z, a solution in the code word in the base code, such that when you compute the parities here for each vertex, they agree as much as possible with the right-hand sides specified by the white tildes. So you're trying to find the Z such that when you compute the XORs for each vertex on the right, it agrees as much as possible. So it's a special type of max k-XOR. And more formally, we have this, and you're asking for the solution to lie on the base code, right? And that could be tricky to enforce. You're already trying to solve a k-XOR, and on top of that, you're asking for a specific kind of solution. But what we can do, and we can relax. You can say that, oh, I would be happy to have any solution in the base space in F2 to the N, as long as it's nearly optimal for that CSP. It behaves as a nearly optimal solution. I would be happy with that. And now let's see why that's enough. And it's going to be self-correction, essentially. So here we have this Y star. It comes from the direct sum of some Z star in the base code, right? That's the code word that we'd like to retrieve. And the claim is that if the paired sampling property, if this collection W is a strong enough paired sampler, then this approximate solution up to some technicalities is going to lie in the unique decoding ball of Z star. And once you have this property, we are done, right? You can use the unique decoder of the base code to self-correct all the way to Z star. So the moral here is that it's enough to find an approximate solution, Z tilde, like this in F2 to the N, and then you use the unique decoder to self-correct. Very good. So far you have seen this connection of solving a KCSP, solving a max k-XOR instance, with the decoding. If you can solve a max k-XOR, you can also decode for direct sum codes. And you might be asking, why should we hope to solve those max k-XOR? They are hard to approximate, NP hard to approximate in general, right? And the difference here is that you are going to be dealing with more structured instances, pseudo-random instances, satisfying a notion of high dimension expansion. Okay? And to define this notion of high dimension expansion, we need to introduce some notation. So suppose that we have the collection of all walks, here W, and we are going to look at a segment, a segment between A and B. We have two indices between 1 and K, and then you're going to look at this segment. You're going to look at the restriction of the tuples from IA all the way to IB. So this defines the set, WAB, and we can define a natural operator now with this notation. So if you are given three indices, A prime, and B, and then we can form an operator in which the rows are indexed by elements in WA prime, the columns are indexed by elements in A prime plus 1B, and we have two tuples. So suppose that we fix a row here, we fix a column here, and we are going to put a 1 here. If and only if you concatenate this tuple with this tuple, it belongs to the larger collection AB. If you concatenate the two, they would belong to WAB, otherwise we'll put a 0. So we have this operator. And the notion of splittability is as follows. If k is equal to 1, we declare the collection to be splittable. There's nothing to do. Otherwise, for all possible combination of indices A prime and B that are well defined, we look at this operator, we normalize it to have maximal singular value 1, and we ask for the second largest singular value to be at most tau. And if you have this property, we call it tau splittable. Okay, so very good. And this definition first appeared in Mosel. We rediscovered it later. And you might be asking for examples, and the collection of short walks is an example of a splittable collection. And more important for us, a simple modification of Ta-Shma, Ta-Shma's construction is also tau splittable. And that's what's going to make solving the max k-XOR tractable in our case. Okay, and what was the previous approach? So in the previous approach, to solve this case SP, we used sum of squares. We used the sum of squares hierarchy. Let's take a look at a few parameters. So what we had before is the solver. If you have a KXOR instance that was expanding, was tau splittable, we could approximate it well. And in terms of more concrete parameters, if tau was sufficiently small, and here the dependence is not as nice as exponential k, we get an additive approximation of the optimal solution. And also the running time is polynomial, but it's not great. It has those parameters in the exponent. Okay, so that was the machinery that we were using to solve those KXRs. And now let's move to the current approach, the pseudo-random approach. And we need to do things in near linear time. So we need to be more careful with our running time. But we are essentially replacing this part of the approach. And what we get is a better dependence already. So here we only require tau to be to depend polynomially on those parameters. We already get a nice additive approximation. And the running time is near linear. So here we're hiding polylog factors, and you're also hiding a dependence on delta. Okay, so you need to introduce a bit of notation, and this is going to be a cut matrix. So the picture is very bad. So I think that it might be easy to remember the notation after this bad picture. So we have two sets, S and T. And we can look at the tensor product of the indicators of S and T, and this is going to give us some rectangle, right? A rectangle of ones, and everything else is going to be zero. So that's a cut matrix. Very good. And before I go to our setting, let's recap what Fries and Cannon did in the 90s. So they are trying to understand CSPs or like next cut in dense graphs. So let A be the adjacency matrix of a dense graph, and suppose that we can find a decomposition as a linear combination of cut matrices. We can write A approximately, in some sense that we are going to describe, as a small sum of cut matrices. So it's very important that the number of terms here is small. That's a small rank solution. And we also want A and its approximator to be indistinguishable with respect to cut matrices. So here, as we take the max of the difference between A and its approximator, with respect to the inner product of 1S and 1T, this is at most delta n squared. And notice that this here only makes sense for the dense case. Very good. And why is this useful? So suppose that we are given this nice approximator with the previous guarantee, and computing max cut now is an easy task. Is a simple thing to do, because if you count the number of edges between S and S complement, this amounts to this analytic expression of taking the inner product of A with 1S tensor 1S complement. We already said that A and its approximator behave similarly with respect to inner products with cut matrices. Very good, so you can replace and incur some small error. And we use linearity. And we have the inner product of these two cut functions. And it happens to be the size of the intersection. So it's the size of the intersection of S1, L, and S, and S2, L, and S complement. And then you sum all of them. And that's extremely convenient, and you're going to see why. If you take in our cut matrix decomposition, if you take all those sets and put them together and form this Venn diagram, it's going to partition the space n, 1 up to n, into regions of the same intersection pattern. So this will be one region, another region, another region, another region, and so on. We call those region atoms. So and it's easy to see that the number of regions is at most exponential in L. And if L is small, this might be very small. And if the error is a constant, the number of regions is also a constant, right? And what is very nice is that now suppose that you are interested in finding some set S. And so suppose that instead of having S, we are told the fraction of elements of this region that belongs to S. So we have this eta 1, the fraction of elements of this region that belongs to S, and so on and so forth, so on and so forth, so on and so forth. Okay, so if you're given all those fractions, then since the regions, the atoms, they are disjoint, it's clear that we can always realize a set. There's always a set that corresponds to assignment of fractions to the regions. And conversely, if you have a set, it gives rise to some fractions in the regions. And what is nice is that to compute those intersection here, the only thing that we need to know is the fractions, is the values of the fractions. And since there aren't too many regions, what we can do, we can brute force over a discretization of fractions. We can consider a good enough mesh of all those fractions, and then this allows us to estimate the size of the cut reasonably well. Okay, very good. And Oveis-Garan and Trevisan, they extended those results that were for the dense case of Friesen-Cannon to the sparse case for expanders and even low threshold rank graphs. And in our case, we are dealing with this higher order collection of tuples. So the tensors are natural in our case. So the matrix will be a two tensor. Here we need to look at k tensors. So if you're given this function g, you want to find, as before, in the same spirit, we want to decompose G as a sum, a small sum of cut tensors here. And we still want this number to be small, and you want to be indistinguishable with respect to cut tensors. Okay, distinguishable with respect to cut tensors, and now we want the error to be at most delta times W. If W happens to be sparse, this still works in the sparse regime. That's what we need. So we are really looking for the composition in terms of tensors. And what we can show is that if W is a tau splittable collection, and tau depends polynomially on delta and k, then we can find this decomposition. Okay, very good. And to solve a case SP, which is our case, a similar strategy of before would work. So what you do, you take all the sets and you form this Venn diagram. Now, instead of having two sets per summoned in the decomposition, you have k. You may have extra sets, but the strategy is the same. And Friesen-Cannon already observed that it works for KCSPs. And here we observe that even for list decoding, this is helpful. And you might be wondering why on earth we should have a decomposition of this form at all. And showing an existential result is not too hard. It was already done in a beautiful abstract framework of Rangel, Trevisan, Tussiani, and Badan. And what they have is they have a function class that they want to fool, and in our case is cut functions or the negations of cut functions. We have a measure, but let's not bother too much about this measure. And you are given the function that we want to decompose. H is our current approximator, starts with 0. And as long as there is a function in the family that can distinguish, that can see that G and H, they are different, right? If this inner product is at least delta, and what you do, you add this function to H. And if this procedure terminates at all, it's clear that it satisfies the property that we want, right? The correlation with functions, cut functions, is going to be small. But why does it terminate? And that's not too hard. If you track the L2 norm of the difference here, the claim is that it decreases at each iteration. So now let's compute the norm squared, the L2 norm squared, after one iteration. And then this can be rewritten in this form. And here we have a cross term and this other term. The first observation is that f is a cut function. So its L infinity is 1, and then this norm is 1 as well. And this part here, since it's a cross term, and we had an iteration, it was chosen so that this is greater or equal than delta. So you get that this is greater or equal than delta, and minus 2 delta squared plus delta squared, we should get a minus delta squared. So it decreases, and it started bounded and decreases, so it terminates, and when it terminates, it clearly gives what we need. And now the more interesting part is to make all of this algorithmic and also running near linear time. So that's certainly the more interesting part. And we are going to discuss some of those ideas at a high level in a simplified form, but hopefully giving a lot of the intuition. And the goal is we have this function g that we want to decompose. Decompose it in one shot in tensors like this may be complicated. So you're going to have an iterative procedure that breaks this big function, this space, into a 2-tensor, 3-tensor, the sum of 2 tensors, 3 tensors, and so on. So at the first step, you're going to have a summation of this form. This first function lives in a small space, whereas the second part lives in a bigger space. So it's as if you're breaking the space W in a rectangle fashion like this. Okay, so the first part is already small, and the second one is possibly quite large. And then we do it again. Now we want a sum of 3 tensors, and to do that, we are going to use the previous guy that we had. And very good. So we have the sum of 3 tensors. Now the first 2 components are small, and possibly the third one is large. And we continue in this fashion until we have a function that's a full product of functions over a small space, each one of them. So that's going to be the high-level strategy here. And let's see how to implement this, a rough sketch of how to implement this. Well, suppose now that we are in the STF step, and we have the function from the previous step. So the function of the previous step has this product structure, and you want to create a new function that has an extra product structure. So it's as if we want to break this last part here into 2 to have our new function. Not quite that, but in terms of tensors, it's as if you want to split this part of the tensor. And very good. And we can bring again the weak regularity decomposition, but we can try to make it more concrete this time around. So the function that you are trying to look for is a function that in the last part of the tensor here, it's split. Okay. All the functions f, they are going to live in a small space, and this guy lives in a slightly smaller space than the preceding one. And if there is large correlation, then we do the same strategy. But the critical thing is, can we find this function f? Can we make this step efficient at all? That's the crucial thing. And it can be tricky, right? We have many sets to find at once. Why should we be able to find all those sets? And we can ask Merlin. So suppose at this point that Merlin tells us all but the last 2 sets. So we have S1 prime all the way to S minus 1 prime. So we have all the initial segment of sets. And let's see if that's helpful. And that is going to be indeed quite helpful. But we still need to find two extra sets, right? The 2 last sets is up to us to find. So Merlin told us the other sets, and we are trying to solve this optimization problem, right? Of trying to find those 2 last sets. And it has a product structure. So we compare this indicator with this indicator, the second one with this indicator. So we get this product here, and that times the coefficient. And whatever it is, we can, since we have the sets Si prime that Merlin gave us, we can compute this inner product, which is the size of the intersection of these 2 sets. And we can declare this whole thing to be some coefficient gamma L. Okay, so this whole thing is a coefficient gamma L. And then, okay, we can move inside those coefficients again. And what we have here, we can interpret it as a matrix, as a 2 tensor again. And that's very good, because when you look at this problem, seeing M as a matrix and trying to find the best cut matrix for this inner product, this is a well-known problem. This is a cut norm optimization problem. And it has an STP-based approximation algorithm by Alan Auer. So that's great. And another thing that's not evident from what we have discussed is that M, this matrix M, is going to be quite sparse. So even though it potentially lives in this large space, the number of non-zero entries is only linear. And we can now use sparse SDP solvers that take advantage of that to run near linear time, such as Aurora and CADA. So that's precisely what we're going to do. And now let's go back to this point. Do we really need Merlin to tell us all those sets, all the initial sets? And the answer is no. Archer is enough. You don't need special non-determinism to guess those sets. And why is that? The reasons that is a similar reason from before is that this collection of sets is low complexity. We don't have too many sets in our collection. So when you form this Venn diagram, it doesn't have too many parts. And then what we can do, we can use the fractions as before and brute force over all of them. And that is still not too expensive. So that's sort of the beauty of this weak regularity approach. Okay. And so we don't need Merlin, we can do this step ourselves. Very good. That's all. Thank you very much for your attention, and I'm stopping here.